So I'm Mike Saunders, Principal Consultant at Red Siege. Today we're going to talk about what is shellcode and why do we need to hide it, and some ways that we can do that, and then a few other ideas that go along with that at the end. So what is shellcode? So shellcode is a small piece of code that's used as the payload. Now, traditionally, shellcode was something that we would inject as part of like a remote code execution exploit, like a buffer overflow. And it created a command shell, hence the name shellcode. More often now, when we're talking about shellcode, and what I'm talking about specifically here is a shellcode loader. So something that's going to load my C2, whether that's Cobalt Strike, Brute Retell, something like that. So how do I protect my shellcode? And we're going to talk about why I need to protect that. You can store shellcode as hex. We typically see it as hex, but you can store it as an int. You can store it as a raw blob of data in your payload. So the examples that I'm going to show you here, the way that I ran these tests is I didn't want to have my code execution mechanism possibly be the thing that's getting signatured. So in all of my examples, they contain obfuscated shellcode and a routine to deobfuscate that shellcode and print it out to the routine. Then I uploaded those samples to VirusTotal to see how they scored. So there's what you're seeing on the detection rate here is either the shellcode being detected or the decoding mechanism being detected. We're not doing any execution. So that's what these detections will be based on. So why hide? Has anyone ever used a Metasploit payload, didn't take any obfuscation techniques, and got busted by antivirus? Right, so you know the pain. You know that shellcode is going to get, or that executable is going to get detected. And we want that to not happen because we want to hide. So if you aren't writing custom artisanal shellcode by hand, you're probably going to deal with detections. If you are doing that, you probably don't have to worry about obfuscating your shellcode as much because there's probably no detection for your custom C2 yet. So this is an example of a Meterpreter reverse HTTPS or HTTP payload, no obfuscation in my test program. And these last bytes that are highlighted are just the last bytes of the shellcode for that Meterpreter payload. And I got detected. In fact, I got detected by 27 of 72 agents on VirusTotal, which just straight unobfuscated Meterpreter shellcode, only 27 of 72 agents detected that. Like, one, I was like, wow, that's pretty bad, 27 detected. And then I was like, but there's like 50, 60, 45, whatever the math is on that didn't detect it. That was kind of sad. So there are different ways that we can hide. We can encrypt our shellcode, we can encode our shellcode, or we can otherwise obfuscate it. Some of you might be like, but Mike, why do you have your shellcode in your shellcode loader? Because it worked for the concept of this talk. You could separate it, but you probably still have to deal with the detection issue. But all of the examples in here, the shellcode is in the example program. So base64 encoding. Base64 encoding is probably the most simple obfuscation technique that we could use. There's no encryption, it's just encoding. And 18 of 72 engines detected that. So I wouldn't recommend this, but also, man, only 18 and it's only base64. Like this, you can't get much simpler than this. But we could go old school encryption. I'm talking old school. Let's go back 2,000 years. So anyone ever heard of a Caesar cipher? Also known as a rot cipher, like a rot 13 is what we hear about the most. So all you're doing with a Caesar cipher or a rot cipher is shifting the alphabet. So if I have an A and I rotate it by 13, I come over here and I end up being an M or an N, whatever that number is, but I add 13. So I do the same thing to my shellcode bytes if I wanted to use rot 13. It's 2,000-year-old cipher. And, it's been around a long time. If I want to use my shellcode at runtime, I take my encrypted shellcode and I subtract 13 bytes from each byte of shellcode, and now I have my regular unencrypted shellcode. Any guesses as to how well this performed? How many out of 72 engines detected rot 13? 15, 5, 2, 7. Rot 13, this isn't even like rot 17 getting cute. It was 7. Side note, one of our guys was on doing a web app pen test, And he's like, this looks really like ROT 13, but the data wasn't decoding. And so like he just like brute forced it. It ended up being like ROT 17 that they were using to encrypt the data in the web app. So that was fun. But 7 of 72. 7 of 72. This encryption routine has been around since well before computers were ever invented, from the time of Julius Caesar, where it gets the name the Caesar cipher. And only 7 of 72 engines detected that. That's kind of sad. So we could have more modern encryption. We have things like XOR or XOR. I don't know how you want to pronounce it. I'm going to call it XOR. XOR with a multi-byte key, AES, ARC4, Blowfish. There's all kinds of encryption. We're going to look at a few. This is probably the most simple that you could do. It's a XOR. And so what happens is you iterate over your shellcode, and for each byte of your shellcode, you XOR it with the key. And the fun thing about XOR is that when you XOR something, you encrypt it, and if you XOR it with the same key, you get the plain text again. So this is a very simple encryption routine, and it would be pretty easy to brute force those signature bytes, right? Because every C2, Metasploit, whatever, has a certain pattern of bytes that are signatured. So you would think they'd be able to pre-compute every possible value because there's only 256 values for the key, right? And yet, only 8 detected it. Like, that's kind of like, it's not ideal if you're trying to hide perfectly. Only 8 detected it, but 8 did detect it. So let's do XOR with a multi-byte key. So, and for those of you who are newer and you're like, man, I need to know so much, I've been using XOR with a multi-byte key for a long time, and I never really thought about how it works. The way it works is not that you XOR each byte with like the key. You XOR the first byte with the first byte of the key. So if your key is ABCD, you XOR the first byte of shellcode with an A, and the second byte of shellcode with a B, and the third byte with the C and the D, and then you repeat the key. And it wasn't until just a couple of weeks ago when I was putting the slides together, I was like, wait a second. Mike, that's not how it works the way you think it works. So I've been in security a long time, and I did not actually realize how that worked. I just like knew it worked. So take that. So this is how you do XOR with a multi-byte key. You have if you laid your shellcode out, and then you wrote the key underneath it, the key would just repeat all the times until you had the same number of bytes. Only 2 engines detected XOR with a multi-byte key. Now, we'll talk about later, there's a little caveat with this because the routine is detected by some engines, but you can change that. We're going to talk about how to break that routine detection later. But only 2 detected XOR with a multi-byte key. So pretty simple encryption and very effective at hiding. AES is much stronger, right? We should use AES. And yet 8 detected AES. The reason 8 detected is probably entropy, and we're going to talk about entropy a little bit more. It's going to be high level. Don't worry, we're not getting into super math here. But 8 detected that, and it's probably because of the randomness that's introduced with AES. On a side note, if you're using AES, one thing you can do to build in a delay, like has anyone ever tried to sleep for a period of time to do AV evasion? I'm seeing heads nod. So what happens is, some AV and EDR have this observation period. They're looking for things to happen in a certain order in a certain period of time. And if you wait longer, they'd be like, this is too much of a performance impact. I'm noping out. So put your AES encrypted shellcode in and put your key, but leave the last 2 bytes off, and then brute force the last 2 bytes of the key. Like that takes, even on my laptop, pretty powerful laptop, takes about 5 minutes for that to run. On slower computers, might take 10 minutes. And now you have effectively introduced this long delay that a lot of EDR is going to be like, nope, I'm going to let it pass. It's taking too long. And they don't hook sleep, because what happens when they hook sleep, they basically see a sleep function. They're like, nope, that's not happening. We're making that now. And so whatever time you said you were going to sleep didn't happen. Your program thinks it slept, but the AV is like, I see what you're doing. So this is a fun trick. This is something you can do. So ARC4, RC4, has in Windows, there's this DLL, ADV API 32.dll, and it has 2 undocumented functions. One is system function 032, one is system function 033. Ostensibly, one of them is for encrypting data, one of them is for decrypting data. But for some reason, much like XOR, you can use either of these interchangeably. And now you have this function built into Windows to give you a different encryption routine. You don't have to write your own or import a large library. It's built in, and it gets used a lot by Windows, so it's something that might be a little less suspicious. Not terrible. 7 engines, less than 10%. 7 of 72. So that's not bad. So what about 2 arrays? So this is something that my coworker, Justin Paul, proposed. So you have 2 arrays. Normally we store our shellcode in one large array. But let's store it in 2 arrays, and let's break it up by even and odd. And I'm not talking even and odd based on the shellcode value, talking about even and odd based on the index within that array. So the first position in an array is index what? 0, because computers. So we're doing 0 indexed arrays. So the first byte of shellcode, 0xFC, is going to go into the even array because 0 is even. And the second byte in position 1 is going to go into the odd array. The third byte in position 2, fourth byte, so on and so forth. So now we have our shellcode in 2 arrays, which hopefully this is going to break up the signature and those bytes won't be detected because they're not contiguous in the shellcode. Again, not terrible, not great. So this routine is probably signatured. The theme for most of this is the routine is probably signatured more than the obfuscated shellcode. I didn't go into deep depth testing that to tell you whether or not that's actually true, but based on what I've seen from some limited testing with some of the routines, changing the routine a little bit, throwing in some junk code to break the signature, reduced the detection rate. So this might be based on the routine. So that tells me it's probably been seen in the wild. If there's a signature for this routine, it's probably been seen in the wild. So if you look at VirusTotal, you'll see it tells you all the engines that detected it. So if you know what your target is using, you don't have to use the best obfuscation method. You just have to use the one that's not detected by what your target is using. So that's why I'm talking about all these different techniques, because they don't work against every EDR for the most part. So what about flipping the script? What do I mean by flipping the script? So if we take the first byte in position 0, let's put it as the last byte of the array. And the second byte, make it the second to last byte of the array. So we're just going to have the array in reverse byte order. Does it work? We'll take a look. This is what the code would look like. Like we have our shellcode variable, and then we're going to read our reversed payload from the end, and then append all of that to the starting at the beginning of the array, and that will reverse our shellcode. And there are probably more elegant ways to do this. Someone asked me yesterday, like, hey, Mike, why didn't you use a hash table with this? And it's because, like, I barely know how to program. Like, I got this to work, and I'm going to stop now. Reversing it works pretty good. Like, surprisingly well. Only 4 engines detected that at the time I did this testing. So what about taking the entire string and reversing it? So now it's not bytes of shellcode. Normally shellcode is in an array, right? So we've got an array with these positions that are indexed. Let's make it a string. We can't use it when it's in a string. We're gonna have to convert it. But let's make it a string. So it's actually backwards. This is the last byte of shellcode, 0xD5, 0xFF, 0x56. Let's make that a string and put it backwards and see if that works. Then I've got a blog series that this talk was based on, and I'll give you the link to that later. You can actually see how it works to convert this back into shellcode. Unfortunately, not very effective. Like, that was surprising to me, but I guess it shouldn't be. So 13 detected that. Not great. What about camouflage? Let's make it look like something else. So if everyone here is wearing a Red Siege t-shirt, only the Red Siege employees know that you are not a Red Siege employee. Everyone else is like, that person worked for Red Siege, that person, or Black Hills. We see lots of Black Hills shirts. We don't know who works for Black Hills, and we're all wearing their stuff. So let's make our shellcode look like someone else's stuff. So a UUID or a GUID, a GUID, a universally unique identifier or globally unique identifier, is a 128-bit label for information. So it's a way in this 128-bit key space, in theory, we should never have a collision. So if we were numbering people in a database and we use a UUID, we should never have a collision. We won't run out of positions, or we won't run out of identifiers. So UUID is a 128-bit label for information. Back in 2021, might have been NCC Group. I can't remember who were the analysts that found this, but the Lazarus Group back in January, the Lazarus Group was using this novel shellcode obfuscation technique and a novel shellcode execution technique and a novel technique for copying shellcode. So if you don't know in a shellcode loader, there are like 3 patterns, right? You have to allocate memory, you have to copy your shellcode into it, and then you have to execute it in some fashion. So this will all come together. You'll see why they use this technique. So a UUID has a specific format. Starts out, you got 4 bytes, 2 bytes, 2 bytes, 2 bytes, and then I think that's 6 bytes left over. And it needs to be structured in a specific way. You could take your shellcode and just break it up into that format with the dashes in between it, and it looks like a UUID, but it doesn't function like a UUID. This actually functions like a UUID, and why will become important in just a minute. But Bobby Cook, what is it handled? Boku7, Bobby Cook is super smart guy, wrote this tool for Cobalt Strike loader called Ninja UUID Runner. And you can see here what actually happens to the shellcode bytes. So these is like the first 16 bytes of shellcode here. We see that FC, which is the first one, goes here, then 48, 83, 84. So the first 4 bytes are reversed. And then the next 2 bytes are reversed. And then the next 2 bytes are reversed. I don't know if the zeros are reversed or not, because they're zeros, I can't tell. But then these are in the right order. So there's a specific format. And the reason for that is this nice trick. There is a code, there is a API called UUID from string A. And what it does is it takes a string UUID from string, and it converts it into binary. But the reason Lazarus Group used this is because UUID from string A takes a string UUID, converts it into binary, and copies it into a memory location that you specify. So if I have to allocate memory, copy shellcode using RTL move memory, RTL copy memory, Marshall.copy, something like that, it's a very well-known execution pattern. So even if nothing else about your loader is detected, that pattern can be observed and can be inferred that this is a shellcode loader. But now if I use UUID from string A to copy my shellcode into memory, I don't match that pattern. So if everything else is good, I've now broken that pattern. That's one less thing that they can detect me on. Unfortunately, people know about it. So this one, they probably wrote a lot of detections after Lazarus Group dropped this technique. But there might be other data formats that we could use to hide our shellcode. And in fact, there are. We can store our shellcode as an IPv4 address. So we convert our shellcode bytes into integers. And then we store an array of IP addresses. We could store it as an IPv6 address. We don't even need to convert. We just structure it with the right colons in the right places, and now it's an IPv6 address. What also uses hex as an identifier on our networks? MAC addresses. We can store it as a MAC address. And in fact, there are some helpful routines. RTL IPv4 string to address A, IPv6 string to address A, and RTL Ethernet string to address A. And all of these, whether I did IPv4, IPv6, or MAC address, only 6 engines detected that. So I tested all of the possible variations, and only 6 engines detected that. And this technique has been around for a while. There's a suite of tools called Hellshell. I think it's Orca 666 put it together, that has examples of all of these. But the only one that signatures were written for was the first one with the UUID, because that's the one that the Lazarus Group got busted with. So this works. You know, I mean, if all of you go back and write shellcode loaders with this, probably not much longer, but I'm giving you some ideas. So I mentioned entropy earlier. We encrypt our shellcode because we don't want to get caught. But when we encrypt our shellcode, we increase entropy. Entropy is a measure of randomness. And when something is very high in entropy, it's very high in randomness. And if you have an executable that's very high in entropy, some EDRs look at that and go, it's very high in entropy. It's likely that there is encrypted data in this program. And if you have encrypted data in the program, you're probably trying to hide something from me. I don't know what it is, but it's suspicious. And they might not let you run. That's how I learned this, was because I was going up against CrowdStrike, and it would not run my executable at all because the entropy was really high, because I was using AES encryption, because AES is great. It's going to be the most secure one I can use for my shellcode. But when I encrypted, I increased entropy. But I encrypted because I didn't want to get caught. But when I increased entropy, I got caught because I encrypted. My entropy was high. So we've got this catch-22 problem. How do we reduce that? Well, there are ways that we can do that with like languages, with words. Languages, written languages are not random. Like we can measure this mathematically. I've given a talk on it. Like we know that they're not random. They're less random than random data. And because they're less random than random data, if I combine high entropy, high randomness data with low entropy, low randomness data, I decrease the overall entropy. If I decrease it enough, I can get past that threshold. So I came up with this idea of a tool called Jargon. And I gave a talk on this yesterday. You can find the video on it and the slides are available if you want. But the idea behind Jargon is you have a shellcode loader. You have 256 unique words. It needs to be 256 unique words because each word represents a byte of shellcode. So if you think in an array with 256 words, whatever word is in the first position of the array represents 0x00. The second word represents 0x01, and the last word represents 0xFF. So now I have covered all possible shellcode values, and I have words that represent that. And then I go through a loop, I look up every shellcode value, and I build a new array of words. And at runtime, my loader has my translation table and this gigantic array of words that represent my shellcode bytes. And because languages aren't random and I have all these words in my loader, I've decreased entropy. And so now I have obfuscated data. There's no shellcode in my loader, but it works like a shellcode loader, and I don't have the entropy problem. So I would encourage you, if you're interested in that, go check out Jargon. It's available on our GitHub. I wrote the code, so there's probably a bug in it. I know because one of our employees, after like a year and a half of it being out there, was like, man, this doesn't work in 32-bit land. And he's like, you've got an off by one error in your loop. Because, I don't show it up here, but like I suck at programming. And so I had an error and it didn't work in 32-bit code. I was like, I've only been using 64. So if you can find ways to improve it, please do. But this is what it looks like. Let's say I've got 5 bytes of shellcode. These are my shellcode bytes. This is my translation table. Should be 256, but I only needed 5 for this example. So day is going to represent 0x00. And 0x00 is in the second last position. So it's here in our translated shellcode. And so we just go through this loop. So this is what your loader looks like. You've got translated shellcode and a translation table. So it is deceptively simple. Like once you start looking at it, and it's so like unbelievably effective. I couldn't believe that this worked. And in fact, it does. It works really well. Only 3 engines detected that. And part of that was like the routine was getting detected. So it was a little bit higher before, and then I inserted some junk code, and we'll talk about that trick shortly. I also came up with this idea of Jigsaw, which I'm giving a toolshed talk on later today. So if you think about a jigsaw puzzle, right? You've got a bunch of pieces, and you've got a picture on the box. If you've got the picture on the box, it's pretty easy to put the puzzle together. You start, oh, this needs to go here, this needs to go there. But if someone hands you a bag of jigsaw puzzle pieces with no picture, you can still put it together, but it's going to take a long time and it's going to suck. So my wife likes to do jigsaw puzzles, and I was thinking about this idea of obfuscation, and I had Jargon, but I wanted more tools in my toolkit. I'm like, how do I make this work? And so I started thinking about it, and I got this idea for Jigsaw. So let's take this example, 10 bytes of shellcode that's up here. I'm going to use Python to generate my encrypted shellcode or obfuscated shellcode. So I'm using a list, which is kind of like an array in C or other languages. We're going to take a list. I'm going to populate it with a range starting at 0. It includes 10 entries. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to call random.shuffle. So now the array is shuffled. So now this is the order of those 10 bytes. They're in a random order. And what I do to construct my obfuscated payload is I iterate over the positions list. And I append onto my shellcode, my obfuscated shellcode variable. I look up the first value of positions. I see it's 1. So I go grab the shellcode byte at position 1, which is this, because we're 0 indexed. So I'm going to have 48 is going to be the first byte of shellcode. We can go to the next one. It's 6. So I'm going to go 0, 1, 2, 3, 4, 5, 6. I'm going to grab CC and I'm going to insert that. And now my shellcode loader has, it's got my positions. I actually should have the Jigsaw in here, but I don't. But the Jigsaw, which is the obfuscated shellcode, and my map, which is like the picture on the front of the box, the positions list. And I just reverse that process. I read from positions, I grab the shellcode byte that is at that position, and then I insert it into the new shellcode array at this position. And now, so like I don't build it linearly. I have a new array that's filled with zeros, and then I just insert into each position the right piece of shellcode where it goes based on the positions list. You can read more about it here. I've got a blog on it, but it works pretty well. Only 4 engines detected Jigsaw. So again, not perfect, but depending on what you're going up against, it's good enough. So Corey came up with this idea. He called it offsets. We later found out that it's called delta encoding, but Corey Overstreet on our team wrote a blog about it that I've got linked here. But the idea is you take your first byte of shellcode and you store that value. You go to your second byte of shellcode, and now we're going to build a new array of values for the rest of our shellcode. And I subtract the first byte of shellcode from my current byte of shellcode, which is the second byte of shellcode. And I store that value. And then I go to the next one, and I subtract the second byte of shellcode from the third byte of shellcode. You're like, but Mike, what if some of these values are less than 0? If we're using unsigned character arrays, it actually just flips around. When I first did this, I was adding values to it every time, and they're like, oh, I don't actually need to do that because it'll wrap around if you're using an unsigned array. It's one fun thing about math and in some programming languages. So this is what those bytes of shellcode become. I store 0xFC, and then my array of obfuscated shellcode stores the deltas. And that was surprisingly effective. Like, it is a very surprisingly effective technique. Only 2 engines detected that. So that was pretty awesome. So I talked about breaking signatures. So lots of times it's the routine that is signatured, not the shellcode bytes that are signatured. So, if we think about like this, right? Like how we reconstructed, this is the routine that's signatured. This is what they're detecting, is this pattern of moving bytes around. So we want to break that. So we can do that a bunch of different ways. One way is like, so if you're not familiar with like compiling programs on Windows, depending on the tool set that you're using, you can compile a program as a console program, usually like an EXE, it's called, or you can compile it as a Windows system, meaning a windowed program. And you can just change from an EXE to a windowed program, and that has been enough to break signatures depending on what the EDR that you're going up against. Like there's like, oh, this is the same code, but it's not in a console program. It must be okay. And then you just run the program in a hidden window, and no one sees it. You could also insert junk code. Now, if you're doing this, you may need to disable compiler optimization. Compiler optimization looks at your code, says, you know what, you're probably not as good of a programmer as you think you are. I'm going to make this more efficient. And you've got a bunch of code here that doesn't do anything, so I'm just going to remove it. And this complex routine that you're doing here, I can make it more efficient. I can take it from 10 lines of code to 2 lines of code, and it works the same. Which is great. We kind of want that lots of times. If you're not an amazing programmer, you want your stuff more efficient. But when you insert junk code like this because you're trying to break signatures, it's like, you don't need that there. I'm going to take it out. So disable compiler optimization. One of the things you can do is just, oh, there we go. I don't know where it's at on the screen, but printf. But don't print anything out. Like just printf and open and close. Nothing goes to the screen, but something happened. Something happened between like one action and the next action. And because signatures are brittle, if you change that, that can be enough to change the signature. If you're in a windowed program and you have it hidden, print out whatever you want because no one's going to see it. So that's even better. Writing to the null device. So the null device exists on Windows, and we can write to the null device. It goes into the ether. But we took an action in between 2 other actions that we wanted to break up. Writing to the null device could be something that breaks up that signature. I've even seen just opening the null device and closing the null device be enough to break that signature. I didn't even have to write anything. So these are ways that you can break up the signature of those routines, because your shellcode isn't being detected. It's the routines that you use so you can recover your obfuscated shellcode. So I wrote a blog series this summer. It was originally going to be 30 days of obfuscation. I've realized several techniques into this. I was like, I am not doing this for 30 days because I got to write a Python program to obfuscate it. I got to write a C or C# program to deobfuscate it. I got to write a blog post for JCon because he wants content and now he wants videos. So now I got to record a video. And I was like, nope, I made it to 14. That's as much as I got. But there are other techniques that I didn't talk about here, but you can see the two best were Corey's offset technique or delta encoder and the Zohr with a multi-byte key. Jargon 3, Jigsaw's 4 with reverse byte order, and it gets worse from there. But even if something has 8 or 10 or 13 detections, if your target's using a specific engine and you know what they're using and that isn't being detected by that engine, that's good enough, right? Like it doesn't have to be perfect. That might be good enough. So if you want to read the blog series and watch the videos, you can find it at this link here, and it goes into more detail. I also wrote a GitHub repo called Chromatophore that contains all of the example programs used to generate what you saw on the screen here, as well as other ones that I didn't talk about. And so you could take these, like the basics of the shellcode loader is there. The obfuscation technique is there. You just need to get your execution and that now. So those are examples that are available for you. Some other ideas for obfuscation. So steganography. Anyone here familiar with steganography? Okay, most of you are, so that's good. For those of you who aren't, it's the concept of encoding data in an image. Images are made up of a bunch of pixels, red, green, blue, and alpha channel, depending on the kind of picture you're looking at. Alpha controls the brightness of that pixel. So let's take the least significant bit for each pixel and change the value. And we can do that, and we can encode data into an image without significantly degrading the quality of the image. It's not the same image, but it doesn't look like just absolute garbage. It just looks like a bad picture. So steganography is something that we see a lot in some malware type things, and it is something that you could incorporate into your loader. Casey Smith, the GOAT, proposed this idea of storing data as a big integer. So if you're writing your loader in .NET, a big integer is just this gigantic hexadecimal number. What else is gigantic hexadecimal numbers? Shellcode. So making our data look like something else, we stored our shellcode as a big integer. That might be enough, and in fact, it is enough because Casey has proven it, to defeat engines sometimes. Store your shellcode in a resource file, like an icon file. So now your icon's not, or your shellcode's not in the text section of your executable. It's in the resource section of your executable. That might work. Put your shellcode in a separate file altogether that you either pull down from a website or you read off disk with it. Sometimes breaking that up into 2 different places can be enough. For simplicity's sake for this talk, I put everything in the loader, but breaking it up could work. I will say that because of the AV component of EDR that looks at signatures, you probably still need to have your shellcode obfuscated in that separate file. So with that, this is me, Mike at Red Siege. Feel free to reach out if you have questions. I'm on Twitter, LinkedIn, Blue Sky, Threads, Instagram. That's me, Hardwater Hacker up there. Follow Red Siege to find out about new talks that we're doing, the webcasts that we have coming up, things like that. I'm on LinkedIn. You can send a request. We've got a great Discord. I think it's a great community. Lots of helpful people there. We'd love to have you there. We also have this thing called the Wednesday Offensive. It's at 12:30 Central Time. Every Wednesday, we have interesting people doing interesting things in the offensive and defensive security space. It's very discussion-oriented, no slides, no BS, 30 minutes in and out. We're done at the top of the hour. And it's a lot of fun discussions. And you can have your camera on and come off mute and ask questions. Or if you're shy, you can type questions into the chat box. Happens all the time. And we love that. So we'd love to have you there. If you want the slides, they are at redsiege.com/hiding. So the slides for this talk are available now. I am legally obligated by marketing to show you this slide. I now have. So any questions? Does anyone have any questions? Yes, sir. So the question was, with brute forcing the last 2 bytes of the AES key, would that increase in utilization be a possible signature, or would maybe the user notice it? So it's not enough to slow down the computer. Definitely not. There will be an increase in CPU speed, but every action we take has an observability. So it's just a question of what actions do we want to take. What I can tell you is I have never seen that result in a detection. But if you were monitorizing, I was going to say, if you're monitoring CPU utilization on computers and you know that your baseline is this, and all of a sudden for the next whatever, it shot way up to this, that's an anomaly that you might want to investigate. However, there's probably lots of things that cause increased utilization, but you're right, it could be a signature. Questions? Yes. So the question was, have I tried to combine tactics like using jargon and reversing? And I haven't tried it with jargon, but I have done that with techniques. You could take that UUID encoded shellcode, because it's all we did was reverse the order. You could then run XOR with that as well. And that would, you have multiple techniques, and there's definitely nothing wrong with doing that. And you could do that. And I encourage you to test these things before you YOLO them out into production. Some things are going to work and some things aren't. And hopefully you figure out the best possible solution in your lab. And so that is definitely, combining techniques is something you can do. Yes, sir. So the question was, were there surprises in the detection engines? What caught me and what didn't? The big one, where are we? Right there. Like Caesar cipher, like simply rotating our alphabet. Like that, I can't believe that wasn't detected. Because signatures, right? They're just signatures, so they're pre-computed for signature-based detection. You know the preamble for your shellcode loaders for most, Cobalt Strike has this preamble, Metasploit has this preamble, stuff like that. You could easily compute all the possible values and have a signature written for it, and yet a 2,000-year-old encryption scheme was only detected by 7 of 72 engines. So yeah, that was surprising. Any other questions? Yes, sir. Yeah, so the question was, when I was going through this, did I notice any patterns like this vendor was good at detecting this kind of stuff, this vendor was good at detecting that? And that is an excellent question, and I didn't even think to do that. So yeah, mine was not there. But yeah, that's a great question. And I'm sure that there are patterns like that. Some are better at certain things than others, because we see that with the techniques we use to execute shellcode. Some are better at certain things than others. So I'm sure there's a pattern there, but I didn't discover it when I was doing. So thank you very much.